For your data set, how do you know those queries can form a query chain? You collect the data from the same user ID.
Yeah, it's data by the same user and sorted by time. And we did some, we had some heuristics to filter stuff that are by 100% not query chains. And we manually selected the chains that seem to be capturing some kind of records. So the answer is manually. That's how we know.
Thank you. I'm David Zadger from the University of Maryland. I'm just curious about the intuition for the sequence of a query chain. Is it that the user is going to get information about the new query that excludes information about the previous queries, or that is more focused towards those topics based on previous queries?
There are different types of checks. Sometimes it is focusing, sometimes it's totally contrastive. There are different types, and there is not necessarily a one correct way to describe it. So there are some are more, as I said, some are more focusing, some are going to completely exclude the information.
Does the user have a way of indicating whether they want to narrow their search based on what they previously searched for or exclude?
No, currently they don't. But we didn't include it.
How would you characterize the difference between the experience the user would have through a query chain versus just dumping all those queries, take all their terms together into one big query?
Well, it's supposed to be like each query is a refinement of the previous query, and not necessarily knowing the direction of the refinement. But it's kind of like the first summarization is supposed to be like a lot more general than the following summarization. So I believe it's supposed to be different than querying all those together, because you will get a different the size of the summarization covering each part of the query will be different when you split it into queries.
So it helps narrow down the amount of things to look at in each step.
Yeah.
Thank you.
Welcome. Thank you.
And thank you for your talk. I'm Lou from Cornell. I have a clarification question. So when you say you use the LDA to build a model, do you mean at each step you build a model based on the all documents you have previously, or you build a model based on new documents?
Partly we run the topic model each time we are presented with a new query, so it's very slow. So yes.
So are you expecting the topic model actually evolve based on what you have at this moment?
And it's not an involvement. We run a totally new process each time. So it's like just running with different clustering of the documents.
But you will assume you have the historical data, right?
We can assume it, but we are not using it in the evolution.
Okay.
We need like when we run the topic model for query 2, we have the information for query 2.
It's basically like just update the topic model.
Update the information for each step.
Okay.
Okay, let's thank the speaker again. All right, our last talk is exploiting pipelines to enhance multi-document summarization and the speaker will be.
Hi everyone, I'm standing between you and lunch, so I'm going to summarize my summaries. So this is work done by my PhD student Jinping Ng and his collaborators Yan Chen and Zhojun Li, Prof. Li at Beihang University. And normally he would be here to present, but he's in the hard place of being stuck between his old job, working with me at NUS, and his new job, and neither of us will finance his trip here. So in any case, let's get started. A fierce cyclone packing extreme winds and torrential rain smashed into Bangladesh's southwestern coast on Thursday, wiping out homes and trees in what officials describe as the worst storm in years. More than 100,000 coastal villages have been evacuated before the cyclone made landfall. And the storm happened to match one in 1991 that sparked a tidal wave that killed an estimated 148,000 people, Kamakar told AFP. So this is actually several sentences taken from the TAC document set, and as you can see, they are quite, the normal breaking news types of things that we like to summarize in news, but also that they happen to nicely fall into background as well as current information. So, for example, you can see the first two sentences, if you can see over here, these are sentences about the current article that correspond to this latest cyclone, whereas the third sentence is really background information. We saw this in Janara's work too, where she said there's cell phones, about people's cell phones going off. This is not really that important. So what we'd like to be able to do is use temporal information that's in the articles themselves to know that that's not important, to rule that out. So the key thing that I want you to remember today is that key time spans are summary worthy. So for example, we might say that what you see from the third sentence is not that important, we can just grade out, and that the fact that the officials describe something later on, that's also not very summary worthy. We'd like to remove that and just concentrate over here on the latest cyclone. So that's exactly what we're going to do. We're going to take newspaper articles, TAC articles, multi-document summarization sets, exactly these artificially 10 documents at a time, multi-documents, only 3 sentences output, okay? And we're going to generate timelines from each document. Okay, so this is Samantha and I have 10 of these, okay? And we're going to derive some very, very simple features that I'm going to argue that all of us in this room can take advantage of and probably do better than we did, okay? And we're going to involve them into a summarization pipeline. And this is the boring extractive summarization, where we create some nice features, we do supervised learning, we feed them into this machine learning engine, which we have no idea what's going on inside, and we got a summary out the back. Okay, so hopefully with that, I've motivated why we want to do that. There's often background information or different types of temporal information in news articles, and that's why we need to incorporate this into the summarization process. So I'm going to talk briefly about the timeline generation process, and then most importantly for this talk, about how we're going to involve that in integrating it both in scoring as also in reordering, right? So our timeline generation process is really simple. We take an input document, and then again, this is done per input document. We do event, which basically means verb predicate. Okay, we identify predicates, extract those. We also identify time expressions, time x's, in the same way that time ML, if you're familiar with that, standard does. Okay, after we've done that, we do our temporal processing, which has 3 steps. First is our event-to-event temporal classification. And then event to time expression, temporal classification, and then time X normalization. And we're going to talk about these 3 steps and then conclude about how we're going to do the timeline generation process. So event temporal classification, this was described in an earlier paper in UMNOP last year by Jinping. And And basically what it does is we're looking at individual sentences in an article. So here we have S1 through S4, 4 sentences, and we're trying to find predicates, verb predicates, and then try to describe how they are related to each other in terms of time. And this is a very simplified version of time relationships that only take into account before, after, and overlap. So it's not as complicated as Allen's time interval algebra. Okay, so we might know that a predicate in sentence 1 comes before B and D, and we might know that B itself overlaps with an event that comes later, 2 sentences later, and also comes before sentence C. But note here that these types of systems that we are doing don't have any way of reconciling transitivity. So the fact that A comes before B, B comes before C, we don't try to infer that A comes before C. Okay. Also, in a previous work in Coling 2 years ago, Junping described another system for relating time expressions to events. So this is a bit simpler, right? We extract a year or time expression, let's say 1991, that cyclone that you saw before, and we're going to locate that in a sentence and then try to describe whether predicates come before or after or again overlap. Okay, so these two systems are a little disjoint. They serve complementary purposes. And finally, we have the time normalization process, right? So, for example, we have a news article. It says June 6, 2014. If we see the word today in that article, we would like to be able to know that it refers to that. So that's a standard task that people have very, very good F measure for, and we don't try to do that ourselves. This is we use the Heidel time system for doing that. So once we have all of these free systems working, what we want to do is generate the timeline that I showed you earlier, and that's done by the following steps. First, we're going to extract these time x's, and we're going to put them on a timeline. So we have exact timestamps as well as relative time spans, like 1999, as you see on the left. Okay, then we're going to place events which overlap the time expressions onto the timeline. So, for example, if you remember the cyclone example, there was the cyclone that smashed and packed houses down. So we have this information located as overlapping with the time expression here. Then we're going to place other events that overlap with the events that we saw onto the timeline. That's a separate step. And finally, try to insert the rest of the events based on before-after relationships that we've inferred from the other steps that you saw. Okay, and that completes the timeline generation process. And there are lots of caveats here that I can go over with you in a question and answering session, but that's the gist of it. So, okay, that's interesting, but it's not the point of my talk, but this is about summarization, right? So we want to integrate summarization, timeline information into the summarization process, and how we do that is incorporated into a multi-document summarization, extractive summarization system. This is the swing system from my group. It's a state-of-the-art, open source summarization system, which you can find on GitHub. It participated in TAC and did fairly well. We did some optimization for Rouge for it. But basically, again, unlike the previous two talks, this is the basic K of n sentence summary, right? We have n sentences in our repertoire. We want to compose a summary of a much smaller amount, K. And it has the standard pipeline of having a pre-processing step. We score the sentences using a variant of LexRank. Then we choose those sentences, we reorder those sentences, and then we output a summary. So where timelines get involved in is two parts, right? First, to create some features that might be useful for sentence scoring, and secondly, to think of how, once we've chosen those sentences, whether they're good or not as a group, whether they play well together, and we introduce a notion of time-based maximum marginal relevance for that. Okay, now I'm going to introduce these three features, but they're really simple. We don't claim these are done very nicely. I'm sure there's going to be later work that can do this better. But basically, the first one is fairly simple, right? Time span importance, and in Singapore, we give everything an abbreviation, so it's TSI. Okay, so TSI basically just means that time spans that have a lot of predicates located in them are going to be more important. So for example, if you see the cyclone example, that cyclone smashed, hit, it destroyed things, all of those predicates are there. That's going to be an important time span. I want that represented in my summary. Okay, so that's all that I do. I take a sentence, I look at the words in the sentence, and I say for each word in that sentence, how many time spans does it, how many events also collocate with the time span represented, and I take the average of that over all the words in the sentence, and that gives me my TSI score. The second feature that we build is contextual time span importance, or CTSI. I'd like to think of this as sort of like smoothing, if you want to think of it that way, in the sense that sometimes we have sentences that are pretty short. They're not at a particular time span that's considered important. For example, this event E, this predicate E is here. But because it's located near important things, we can say, I'm going to smooth out all of these peaks and valleys in this time graph. And I'm going to say that this one here, even though it occurs by itself, is going to be important. So what we do is we search to the left and the right for local peaks. So for example, you can see this complicated formula here. Basically, we have a part that's due to the left and a part that's due to the right. We search for the peaks. The local peaks, this one has a peak of 3, this one has a peak of 2, and we compute a smooth score that contributes to the contextual time span importance. Okay, and this is done again over words that are event words, or in other words, predicates. The third one is pretty simple too. It's some type of coverage density. The idea is that sentences that span a long time or represent a lot of different predicates might be more important. So we're going to do that as well. Let's say, for example, we have a sentence that has 3 predicates, a predicate that occurs in time span A, one that occurs at this point, and another one that occurs in time span A plus 4. So it has 3 predicates in different time spans. Maybe that's a good sentence because it covers all of those time spans together. Sorry. So we're going to try to compute the size of the box, this pink box that it covers, and normalize that over the entire span of the article, as you can see over here. And that's going to be the sentence temporal coverage density, TCD, for this event. Okay, so these are all computed per sentence. These are given numeric values that are fed into the standard machine learning linear regression system to decide whether a sentence is good or not. So the second part is, once we've decided which sentences are good in terms of their individual sentence score, right, we'd like to be able to choose sentences that play well with each other. And everyone, I think, knows about maximum marginal relevance, the fact that we want to penalize sentences that are quite redundant to sentences already chosen in summary. So we thought maybe that makes sense for time as well, right? For example, if we have sentences that are all selecting information from one time span, probably is overrepresented. We want to choose sentences that maybe span more variations. So we want to use time as a basis for doing that, and that's actually fairly easy to do. We're just going to penalize candidate sentences that share many time spans with the selected sentences that are already selected. And the time MMR of a sentence is scored like this. This is the sentence score for that particular sentence. We subtract something for its expected root score. And what's interesting for us here is that we add a component for time, right? So this script T just says how much overlap does this time span, does this sentence have with other sentences that are already selected, right? So if you're introducing some new predicates that happen to be located in a new part of the timeline, oh, that's pretty good. Maybe we want to include that as well. And this, this gamma here is just doing some type of balancing between the standard MMR and the time MMR. Okay, and you can see why that might help, because in fact, if you look at MMR, it's a really useful concept, but the problem is we do it quite shallowly for the most part, right? We look at lexical information, just word overlap to determine that. And you can see from this example that, you know, there's destruction, there are houses that are destroyed, trees that are uprooted, huts that have been damaged, roofs that have been blown off, but they basically say the same thing, but certainly not with the same words. But they appear in the same time span, so we can penalize using this method. Okay, so that's the bulk of my talk. Let's get to the nice stuff on experiments. So we used the TAC data set. We used 2010 for training and 2011 for testing. And I've already enumerated the temporal processing systems that we used. And we plugged it into the summarization baseline that we have from my group. And so we have our basic results here. This is the top row is our baseline swing. And it gets a root score of 0.13. We also looked at another baseline, the Classy system, which performed very well in TAC on the same data set, and we have comparable scores. When we insert the timeline-related features, you can see we do slightly better. It's sort of disappointing. It doesn't do much better than that. It's not very statistically significant, just at the 0.01 level using the student's t-test. And worse yet, when we put in the time MMR, it gets not significantly different at all. So why is that? Well, Jinping went back at my insistence and analyzed what types of problems we might have, and it turns out that temporal processing is, as you probably know, quite error-prone. It's still a new field. We can't generate timelines with a lot of reasonable accuracy. Right? In fact, we didn't even evaluate how good the timelines are that we generate. So because of that, and because of some other caveats that we make in the timeline generation process, these are not very good artifacts that are automatically generated. So we have to make effective use of timelines to make them useful for summarization. So we need to identify which timelines might not be so good for summarization and exclude those for use in the summarization process, and just run basic summarization for those where we think our time information is not effective. And so Jinping introduced this reliability filtering method. It's very, very simple. Basically, it just says that if you create a timeline from a document and there are not enough time spans in it, not enough different discrete pieces of information from it, we're not going to use that in the summarization pipeline. And the reason for that is somewhat interesting. First, it can be because the systems that we are using fail to extract or relate events to each other. But most importantly, the features that we're deriving, the three features that I told you before, are very sensitive when you have very short timelines, because they're always talking about time spans, and we want to have nice long time spans to be able to compute scores that are more fine-grained. When we have short time spans, we don't get that property. We get very extreme values. So the result is we try to truncate timelines that are very short from the process and just use the basic vanilla extractive summarization system for that. And with reliability filtering turned on, we see that actually we still use timelines for over half of the collection, but we still get a very high increase, or at least a statistically significant increase in root score. Okay, but unfortunately, still, time MMR doesn't seem to be pretty effective, right? We saw in row 1 and row 2 that before this filtering, we got a drop in rouge, and then even after we introduced this filtering, where we know that the timelines are being effective, time MMR still doesn't work. What's going on here? Okay, so I sent my student back to the drawing board yet again, and he came up with a solution. He says, Min, actually, rouge doesn't work very well. and we all know that, right? But that's not surprising. So let's take a look at this article. We have sentences 1 and 2 on the top. They're the same. You know, Iraqi reporter threw his shoe at the U.S. president. I can report this is a size 10. And then you can see the left-hand sentence 3 and the right-hand sentence 4. These are the same. So what we're really looking at is this sentence over here, R3 and L4 are the only two differences. And you can see that Rouge scores the right-hand summary better. Okay, we get 0.27 instead of 0.26. Okay, but I'd like to argue that, you know, having what you see on the right-hand side in R3 is probably redundant, right? Because these two names were already mentioned in the first sentence, right? And L4, the sentence over here, gives slightly more information. It's a little bit more varied in importance. So we think maybe that's not so bad. So this opens the floor for future work. Maybe we could involve some type of automated metric that can cater for also time. We're not going to answer that here. In any case, I'm going to conclude this talk. So today I've given you a gist of what's to come. We think that automatic timeline generation is a useful thing for NLP, especially in processing news articles, and we've shown that it helps for summarization. We've integrated it in a first pass in sentence scoring by introducing 3 very basic features which are computable in so many different ways. We've only chosen one method here. And we've also introduced the idea of maximum marginal relevance associated with time, and said that when we're using timelines that are automatically generated, that we need to filter them, because right now that is an imperfect process. So I'm going to make one plug for my student. He is currently looking for a job. So if you have a postdoc position or an industrial position, he'd very much like to hear from you. He's not here today, so I'm helping him out. But if you want more details on his temporal processing, I'd encourage you, as always, to look at his previous papers in Coling and EMNLP. And I have a lot more detailed analysis, but for the sake of lunch, I want to stop here. Okay, thank you very much.
Let's give him 2 minutes of question.
Thank you for a nice talk. I had a quick question about the timeline filtering. So did you measure the increase in precision in any way, or have a handle on how well just that was doing? So if you knew that that precision was a problem before, and this improved it exactly by how much?
Okay, so I don't know whether I can.
Missed it in this slide.
All right. So basically, when you look at rows 1 and 3, these are just the difference when we turn on filtering. We know that we activated the filtering for approximately half of the TAC articles. So that means you know, half of the articles are going through our basic extractive summarization system that's not changed from the baseline, which is row R. Okay, so the increase that we see from 0.139 to 0.141 is basically just half of the data set using timeline features. I don't think that answers your question, though, so can you say that again?
So the question was more about the filtering itself. Did you look at simply the timelines you were left with, or the timelines you were throwing away, to assure yourselves that you were getting rid of garbage? And to what extent could you measure the increase in precision of your timelines, just the timelines themselves?
Okay, that's a really good question. This comes to a limitation of our work, which we didn't actually intrinsically evaluate the timelines that are generated. Okay, so we can't tell whether the timelines that we have are good or not. Our evaluation of the timelines are based on this extrinsic evaluation on the summarization. So we didn't do that.
That's arguably a better way to evaluate, but still I was curious about this. Yeah.
We did some tests that are in our paper that show the effect of the different thresholding, but again, that doesn't really address your question. So unfortunately, I don't have the answer for that. Hope that helps.
Well, thanks for an interesting talk. Mine is a personal question. You talk about timeline being short, but time itself is a relative thing. It depends on, it can be minutes, it can be seconds, it can be years. So what do you qualify a little bit on short? What do you mean by short?
Okay, what I mean by short is in the pictures that I've shown earlier. So let me see whether I can jump to that. Yeah, here. Okay. So what I mean by short is having these dotted lines here. The more dotted lines we have here, the better we have discrete information about different time spans. So these time spans happen as a result of knowing something comes before or after another event. If we have an overlap, then we will have, for example, these three actions all happening at the same time. So even though logically you can think that some of these actions actually come before and after, our inference process is imperfect. So sometimes we are going to combine several events that are logically, to us, inferable as before and after as occurring in the same time span. So I don't know whether that answers your question. With respect to time in different granularity units, we don't deal with that at this point. So for example, this storm in 1991, this entire time span over here might be an entire year, whereas the latest cyclone might be a day long. We don't have information, we don't encode information like that in our timeline generation process at this time. So each of these time spans, all we can say is that the starting time of this time span is earlier than the starting time of this time span. Actually, there are some caveats with that, and so I can quickly jump to that if you'd like. So as I noted earlier, some events span a very long time. Events are just ordered on the based on the start of the duration, and we don't, as I said earlier, try to reconcile contradictions. So we do get some things like A occurs before B, B occurs before C, and C occurs before A. Sometimes those cycles happen, and we don't try to rectify that at this point. So yes, I've managed not to answer your question again, but I hope that helps.
Okay, that's